Hi everyone, here's the second part of chapter 11, and this is on how a nerve impulse passes through nerves. Okay, so nerve cells can either be resting or they can be what we call an action potential. So if they are not transmitting any nerve impulse, they're resting, and then if they are being excited, that's called an action potential. So we're going to look at how all that works. Okay, first thing you need to know is that opposites attract when we talk about charges. So positive and negative attract. And in the nerve cell, there's going to be opposite charges on the inside of the cell and the outside of the cell. And energy is required to keep that separate. And that's the key to the action potential, how a nerve impulse is transmitted. Okay, one thing that we'll talk about is voltage. And this is exactly the same voltage as electricity. So we can measure volts in volts or millivolts. And we look at the difference between like the inside and outside of the cell. And that's called the potential difference or the potential. So if you see that word, that's what we're discussing. We also use the word current in electricity, and that's how much flow there is. So you can think of flow in a river. And then resistance is how much the flow is being limited. So if you have a dam in a river, that's resistance. And so there are insulators and conductors. Insulators have high resistance. They don't let electricity be conducted, and conductors have low resistance, and they easily let electricity be conducted. So all these principles are the same that you've learned about in electricity in the body. There's also this formula, Ohm's law. So the current is a factor of or function of the voltage divided by the resistance. So the higher the resistance, the lower the current will be. Okay, so when we look at potential in cells, the cells have these special ion channels that let ions go through them. If you have a potassium ion channel, it only lets potassium go through. If you have a sodium ion channel, it only lets sodium go through. So they're specific to a certain ion. There are leaky channels that don't have gates. They're just always open, but the substance can only go through if it finds one of those channels. Otherwise, it can't pass through the membrane. And then gated channels can open and close depending on different situations. For example, there are chemically gated channels, and they open if there's a certain ligand, a certain signal that lands on them. Voltage gated channels open when there's a certain voltage, like a certain amount of voltage. And then mechanically gated channels, they have something that physically touches them and opens them. Okay, so chemically gated are ligand gated. This is with a neurotransmitter. We've kind of seen this before a little bit. Voltage gated, if there's a certain voltage, they're going to open or close. And then mechanically, they're actually moving. So an example of that is a sensory receptor. Okay, so these are chemically gated channels. So for example, there's this neurotransmitter here that attaches right here, and it's going to cause that gate to open. And then it looks like it's letting sodium in and potassium out. And then voltage gated channels, they're only going to open if the charge is a certain number, like a certain amount, then they're going to let it open. Okay, so when gated channels are open, the ions flood in really quickly, and it changes the concentration. It'll flow from high concentration to low concentration with the concentration gradient. So the electrochemical gradient is a combination of the electrical and chemical gradients. So when ions flow across, they're going to change the voltage, and I'll show you a picture of that soon. The way that you can measure this is with a voltmeter. So that's how they've measured it. So picture like a little meter that's in the cell and outside of the cell, and it's measuring the voltage. When a neuron is at rest, it's at negative 70 millivolts. Okay, so that's something you need to write down. That's an important number. It can actually vary from negative 40 to negative 90, but in general average, it's negative 70. So inside of the cell, it's the negative charge. That's resting, nothing's happening, the neuron is not conducting an impulse. And when it is that, it is called polarized, okay? So there's different ways that the potential can change. It can be from these channels, or it can be from membrane permeability. So here's what it looks like. This is your voltmeter. pretend that you have a little probe that's inside the cell. This is the tail of the axon. So right here is your axon tail. This is the cell head. These are the dendrites, and then this is the axon endings. So this tail here is your axon. And inside of this, when the cell is at rest, it's -70. And the outside of the cell is a positive number. Okay, so the reason that the inside is negative is because the extracellular fluid has a higher concentration of sodium, and the intracellular fluid has a higher concentration of potassium. They're both positive, but there's going to be slightly less of the potassiums, making it negative inside. So watch that video. So inside here, you're going to have a lower amount of potassium, making it negative in here compared to the sodium. And so how that happens is for every 3 sodium that leave the cell, only 2 potassiums come in, even though they have the same charge. That 3-to-2 ratio is going to make it more negative inside. Okay, so the cell membrane cannot let in anions or cations. It can't let in ions really at all. It can be a little bit permeable to sodium because it's pretty small, and can let in a little bit of K pluses, but in general, you need the channels to let those in and out. Okay, so therefore, potassium diffuses in more easily because the cell membrane does let a little bit more potassium in, so it's going to diffuse, out. It's going to diffuse out more easily compared to sodium diffusing in, so it's going to make the inside more negative. And then you have these sodium-potassium pumps that you might have heard of. These use ATP, and they maintain resting membrane potential, so they keep, like for every 3 sodiums that pump out, 2 potassiums pump in, so it keeps the inside of the membrane negative. All right, so here's your 3 sodiums out, 2 potassiums in, and then also potassiums leak out readily, and sodium leaks in a little bit, but overall, all those things keep it -70 inside when it's at rest. Okay, so then when an action potential is going through the nerve, then it's going to become positive on the inside of the cell. So there's going to be ions moving back and forth, causing the charge to change. So when it's -70 and it's at rest, it's called polarization. When it changes and you get an action potential, it's going to be called depolarization. So what that means is the inside of the membrane becomes less negative. You're going to be more positive. You're going to get up to like +30 inside the membrane. And then hyperpolarization is when it goes like fully to the 30s. So this is like very much not negative. Okay. So if we see this here, this is the resting potential. And then this is depolarization where it goes up a little bit. This is really not enough to cause a nerve impulse, but I'll show you what it actually looks like in a minute. And then hyperpolarization is when it goes below that. Okay, so let's see, graded potentials. These are short-lived localized changes in membrane potential. So these are just in a small little area. The stronger the stimulus, the more voltage changes, the farther the current goes. It's triggered by a stimulus that opens gated ion channels, and it can do depolarization, which we saw the little hump, or a hyperpolarization, which dips below. So here it is. This is just a small area where it's got depolarization just in that one region. The stimulus is right here only. That's a graded potential, just a small patch. No, it's not changing slides. There we go. So depolarization will spread from one area to the next, and it'll just ripple through. So there it is. It's just going to spread. Opposite charges attract, creates local currents, and they depolarize the areas around it. Okay, but it slowly dissipates and decays. It's not like a full action potential. It's just a very small little signal. So here's kind of what it looks like. It just spreads for a small distance and then decays. Okay, action potentials are the main way that neurons communicate. This is long distance communication. This goes between neuron to neuron or neuron to muscle cell. And this is where a reversal of the charge spans the whole axon tail. So you're going to see the whole thing ripple through and change. So it's a lot wider spread than a graded potential. It does not decay. It actually like finishes. Okay. The key players, you've got voltage gated channels. So when the voltage is a certain volt, then sodium's going to rush in and it's going to cause the polarization inside or depolarization inside. And then you also have these voltage gated potassium channels, and these are specific to sodium or potassium. Okay, so here are the main steps. First, you have the resting state where all the channels are closed. You are at negative 70. There might be some leakage, but that's just to keep it at negative 70. So they kind of change places just so that it stays resting at negative 70. There are two types of sodium channel voltage gates. There's the activation gates and the inactivation gates. Activation gates are closed at rest. They only open when there's depolarization, when it becomes positive inside the cell. Inactivation gates are open at rest, and then they keep sodium from coming in. Okay, and then each potassium channel has only one voltage gate, and they are closed at rest. They open with depolarization. Okay, so here's the sodium channel resting state. So this is the one that's closed and closed. And this graph is going to help us to see where the action potential is. When it is peaking, that's when the action potential is going through that portion of the axon. So right now we're down here resting at negative 70. Then you have depolarization. This is when the voltage gated sodium channels open. Sodium comes into the cell and it makes the charge go up in the cell. So it makes it go from negative 70 to something like negative 50. So it's going up by 20 millivolts. So if it can get the charge up to this point, up to about negative 50, that's called the threshold. And that means the action potential is going to continue. If it can't get it up to this amount, then it's going to fizzle out and it won't be an action potential. Okay, so right here is where we are. We're going from negative 70, about here is probably negative 50. That's the threshold. But at this point, this voltage gated channel opened and it's letting in sodium so that it becomes positive inside. This voltage gated channel is closed, so the potassium stays inside. So it's going to stay positive, going to get more positive inside. Repolarization is when that kind of reverses. So the sodium channels are inactivated, the potassium channels open. So the sodium stops rushing in, and now the potassium rushes out, and it's going to drastically drop the charge. Okay, so sodium's not coming in anymore, making the charge more positive, but potassium is going to leave, and it's going to drop it down. It usually drops it down too far past negative 70, so that's going to be the repolarization, and then it'll return back up to membrane potential. So here's what this looks like. This is the repolarization. It drops it down because sodium is no longer coming in, but potassium is leaving, so it's going to make it more negative inside, and then it's going to overshoot it a little bit. That's the hyperpolarization, and then go back up to 70, negative 70. So hyperpolarization is when it's overshooting it. Some potassium channels remain open, and so it like lets out too much potassium. That's why it becomes like negative 80, let's say. And then sodium channels reset. So here you are at the last step. Your sodium channels are resetting. They're not letting any sodium in. Potassium channels are still letting stuff out to make it even more negative inside. So here's the whole cycle. You start with your negative 70 resting, and then it jumps up and becomes positive. It gets up to like positive 30, but the threshold is negative 50. So if it can get past the negative 50, then it'll reach positive 30, cause the action potential right here, and then it'll drop and overshoot it to like negative 80 or 90, and then it'll even out at negative 70. So here's that again. You've got negative 70, depolarization, 55 is the threshold right there. And then positive 30 is the action potential, and then it drops back down, overshoots, and goes back to negative 70. Then it resets. Your nerves have to wait a little bit before they can re-send an action potential. They can't like back to back send action potentials really fast, so they do have to have a minute to reset, and it depends on the nerve and how strong the action potential was. So this is showing the resting membrane potential. You've got to get it back to normal, to the original -70. You're going to pump out 3 sodium ions and pump back in 2 potassium ions, and then it'll make it -70 overall inside the cell. Okay, so once again, once it reaches the threshold of -55, it's going to go further. It's going to go to +30. Action potentials are all or nothing. So if it does not get to that -55 millivolt threshold, then it's not going to do the action potential, and it'll just end. Okay, so propagation is where this action potential is going to ripple down the whole axon. And so what we saw before of the sodiums coming in and the potassiums leaving and all that, that's going to ripple down and happen all throughout the axon. Okay, it's self-propagating. It's going to go on its own. It doesn't need anything to keep stimulating it. It's just going to keep happening. Okay, so here's what it looks like. It's going to start here, and then it's just going to keep rippling down. So right now you're measuring right here, and this charge will just keep rippling down and get positive inside and then dip back down after it leaves. Okay, all action potentials are pretty much the same. The charges are pretty much the same, all of that. But it can tell if it's a strong or weak stimulus because of how many impulses or how many nerves are being stimulated. So here's like a whole bunch of action potentials, and the stimulus, the more action potentials that are generated, the more stimulus you're going to have. Then you have this refractory period. This is what I was talking to you about. This is when the neuron can't receive another action potential. It has to wait a while. So there's 2 types. There's the absolute refractory period, where the sodium has to be reset. It has to be back to -70 to receive another nerve impulse. And then there's relative refractory. This is after the absolute refractory. Most things are back to normal. Some of the K+ channels are still open. Repolarization is still there, and so it's not quite ready. So here is your stimulus. There you are again. Threshold is like right here, and then it goes up to +30, repolarizes, hyperpolarizes, it goes back to normal. Okay, so rate of propagation depends on the axon diameter. If it's large diameter, it has less resistance. Degree of myelination, we learned about that in the last chapter. So how much myelin is on the outside. If there's more myelin, it's going to conduct the nerve impulse better because it's like a insulator. And then you can have continuous or saltatory conduction. So continuous is slow. These are non-myelinated, and they're just kind of continuously getting this impulse. And then saltatory is only in myelinated, and it's like a lot faster. So the myelin sheaths are good. They insulate, and they keep the nerve impulse from leaking. And this is why when somebody has MS, multiple sclerosis, their immune system is breaking down the myelin sheaths, and then that makes the nerve impulse not as efficient, and it loses some of that impulse, and so their nervous system has trouble. So stimulus, size of voltage, as it travels down, it's going to keep diminishing. And so that's because you have like leaking of ions and stuff. So you want this to be insulated so that it's not leaking too much. Here's your voltage gated ion channels. Here, it can let in, these are the little gaps in the myelin sheaths. It can let in the ions and keep conducting the nerve impulse, and it stays stronger. Oh, here, this is what I meant. So these are the myelin sheaths, and then you have the little gaps in between where ions can rush in. So MS is an autoimmune disease, and that's when the myelin sheaths in the central nervous system, not peripheral, are destroyed, and you get these little scleroses, which are like kind of scars, like lesions, So they can see areas where your immune system has attacked that area. Symptoms are visual disturbances, weakness, loss of muscular control, speech disturbances, incontinence. They don't really have very good treatments for it, but they do have drugs that are going to suppress your immune system, so not great. And then they think that vitamin D may help. Okay, conduction velocity. So there's different types of fibers that are going to affect how fast the nerve impulse is conducted. Group A fibers are larger. It's going to go really fast, 300 miles per hour, which is very, very speed happening in your body now. Group B fibers are medium size, and they only go about 30. And then group C fibers are smallest. They're unmyelinated. They go about 2. So if somebody has impaired action potentials, there's going to be some reason, a chemical or physical factor. Some local anesthetics block the sodium gated channels, so that's how they put you to sleep. Cold temperatures can interrupt blood circulation and can affect your neurons too. And that's it.